right, welcome everybody to this wonderful session with an invited speaker. I'm very happy to introduce to you Josh Tenenbaum from MIT. Let me just say a few words about Josh. Josh received his PhD from MIT in 1999, and after a few years at Stanford, he returned to MIT, where he's now a professor of computational cognitive science in the Department of Brains, Minds, and Machines, and also the Computer Science and AI Lab, as I understand. Josh received many awards. I just mentioned a couple. He received the Troland Research Award from the National Academy of Science, and more recently, the MacArthur Fellowship, and many more, which I won't mention here. He's a fellow of the Cognitive Science Society and also a member of the Academy of Arts and Science in the United States. Just a few words about his research. I guess Josh really wants to understand and model how the human mind works, and especially he's interested in common sense development of children and how to model this in machines. So I guess we'll hear a bit about that today with his talk on reverse engineering human cognitive development. The floor is yours, Josh.
Okay, thank you. Can you guys hear me okay now?
Yes.
Okay, my computer is doing some funny thing. I think it should be fine, but if there's a little bit of Zoom interruption, just let me know, I'll see what I can do. All right. I think as lots of people have joined the Zoom room, it's slightly overloading it, but it should be okay. All right, so I'm just going to go to share my slides here for a second. All right, and now can you see the slides all right?
Looks good.
Very good. All right. So thank you very much for inviting me. I wish I could be there in person. I've never been to the KR conference, and I don't, I'm not a member of the KR community, but I think there's something that you'll see that we share very much deeply in common, which is, I personally think the most interesting thing in the world, certainly in science and in the engineering of intelligence and AI, is to understand the nature of human knowledge. What form does it take, and how do we use it? How do we get it? And a knowledge-based approach to thinking about intelligence, which has been at certain times the most dominant approach in AI, and at other times less dominant. I think that is the way to go, and fundamentally all the work I've been doing studying humans from a computational cognitive science point of view, and trying to build more cognitive AI goes in that direction, and points there very clearly. At the same time, the particular kinds of knowledge representations we use and reasoning mechanisms might be somewhat different than many in the KR community have used. As you'll see, I'll try to tell you about the kind of representation languages and reasoning frameworks we use. But I think there's very much deep common cause, and I'm really interested to explore more connections with the community. The work that I'm going to talk about and the work that we do in our group really sits between the cognitive science project of trying to understand how human intelligence works, where it comes from, and the AI project of trying to build more human-like forms of intelligence in machines. And I see these as deeply interrelated, in fact, really essentially interrelated. To me, it's easiest to start off, as I think many of us do, and reflect on the state of AI today. In the broader world, AI is everywhere, and people are talking about a new age of AI and so on. But I think what we all recognize is that we have these kinds of very useful technologies that are called AI, but nothing like the true forms of artificial intelligence practical yet that the field has been interested in since the earliest days. The idea of some kind of flexible, general purpose, common sense system that doesn't have to be built by a dedicated team of engineers who build a big data set and then train something on that big data set, but rather a system that understands what it's doing, can set goals, can think for itself about how to do any one of these very impressive things that, we used to think machines couldn't do these. Now we have machines that can do any number of impressive things, but no general intelligence that can do every one of them like the human mind is able to. So thinking about those gaps motivates the work that we're doing. And again, I don't think it's going to be controversial in this community that what's been driving recent successes on the AI technology side are various advances in pattern recognition and function approximation, broadly machine learning, especially recently in the last 10 years, deep learning. But there's a longer story of machine learning and really making pattern recognition and function approximation work on an unprecedented scale. And it's impressive what you can do with that. But from a human intelligence point of view, there's so much more than just pattern recognition. And in particular, we're interested in all the cognitive abilities that you could group under the heading of modeling the world, all the ways that our minds don't just see patterns in sense data, but we can explain and understand what we see. Our ability to use these models to imagine things that we could see but haven't yet, maybe things that nobody's ever seen, and then to make plans and solve problems that come up along the way as we're trying to execute these plans, all that's needed to make these things we imagine real. And then thinking about learning as model building, building new models as we experience, both learning from our successes as well as our failures. And learning not only from our experience, but learning by sharing our models. Learning, a lot of what we learn as humans comes from what we get from other people, um, socially or culturally. That means within our individual interactions or knowledge that accumulates over time and across groups. So the goal of the work that we've been doing is to try to reverse engineer these abilities, these human modeling abilities. And we're very far from achieving that at the scale that the tech industry is going to put into your products tomorrow. But we're making actually surprising steps. And or to me, I'm surprised at how rapid and impressive the progress is, both on the science side and increasingly on the engineering side too. So I'm going to try to give you a sense of both of those things. But I think from a basic science point of view, if we could even capture the intelligence of just a young child, not to mention an adult, it would be extremely valuable. And in many ways, this is AI's, I think, oldest dream. Um, the question of could we build a machine that grows into intelligence the way a person does, that starts like a baby and learns like a child? It's not just the dream that I'm talking about. It goes back to the very earliest days of the field. Many of the field's AI's founders have embraced some version of this idea. Maybe most famously Turing, in the same paper in which he introduced the Turing test, he also suggested a developmental route as his best hypothesis of how we might build a machine that achieved human level intelligence by starting off building something presumably simpler, like a child's mind, and then teaching it the way we teach children. And he had a number of very prescient ideas in that paper. I'm not going to rehearse all of them here. I'm just going to highlight one key sentence, which I think both gets something very right and also something very wrong. As far as saying, why should we start off by building a machine that starts like a child? Presumably, the child's brain is simpler in some ways. It's something like a notebook, as one buys it from the stationers, rather little mechanism and lots of blank sheets. And here, Turing is giving his own version of what's sometimes called the kind of blank slate hypothesis. That's not exactly, I mean, that oversimplifies what he actually thought, I'm sure, and what he wrote in this paper. But he emphasized the idea that presumably the reason to do this is that children start off knowing relatively little, and thus what we have to build is relatively little. Also, the learning mechanisms implicitly might be some relatively simple and general purpose mechanisms. Especially, it's not so much Turing, but other people who've been inspired by this vision have suggested we should both start off with very little and have, try to have some very simple general learning algorithms, like, for example, a reinforcement learning approach. Although for Turing, it was his approach to learning was more like, I think, what I'm going to talk about here. But what we've learned since Turing, Turing could only presume what the child's brain was like, but we've learned all the ways in which these very simplified assumptions are just not right. I'm pointing here in this slide to work by a number of my colleagues in developmental psychology. For example, Elizabeth Spelke and Rebecca Sachs, who study the brains and minds of very young babies, like 2 and 3 month old babies. They're about the youngest that you can study scientifically. And they've shown, both by studying behavior and by doing brain imaging, that there's a lot already built in. So it's not just a blank slate. Okay. And I'm going to focus a lot on what kinds of knowledge representations seem to be built into the brain as early as you can look in some protoform. Okay, and this is what Spelke calls core cognition, right? And I'm going to talk about ways in which we're trying to capture that with certain kinds of structured knowledge representations and reasoning, especially probabilistic reasoning. Also, we've learned a lot about learning. Learning isn't just, copying things down from what the teacher writes on the blackboard, or soaking up statistics, or learning from, massive amounts of trial and error. As scientists like Alison Gopnik or Laura Schultz have shown, and argued in what they sometimes use the slogan, the child is scientist, children's learning is a much more active, thought-driven, model-driven process of building mental models of the world, or intuitive theories that are like analogs of the scientists' theories that capture the causal structure of the world, that explain what we see. And then learning is more like the way scientists build their theories, by doing experiments to test hypotheses, or seeing surprising findings and then trying to see, how do I change my theory to make sense of what I'm seeing. And I'll talk a little bit about how we're trying to capture these kinds of smarter learning mechanisms also in algorithmic forms. So I'm inspired by these folks. I'm lucky to collaborate with them. And the role that I play in this broader research program is to try to capture these ideas in computational terms. So I'm going to start off telling you about the kind of frameworks and models we've been building to capture this early state, core cognition, and a focus on abilities like intuitive physics and intuitive psychology, which are aspects of common sense that are present again in some kind of proto forms as early as you can look, even in 3-month-old babies. They develop in really interesting and important ways over the first few years of life. I'm going to show you a couple of videos here to make this concrete from 1.5-year-old babies. Um, but that's just a convenient stage, and this is, absolutely, this knowledge is absolutely central to human common sense. It's different from the common sense reasoning approach that I think, some in the KR community have traditionally studied, or another long tradition in AI, the idea that, like, common sense is all the things that adults know in order to, read the newspaper, or read a Wikipedia article, or understand, communicate in language. That's ultimately where we're aiming. But where human common sense starts is what's present before language and what language builds on. I'll come back to language a little bit at the end, and we can talk about that in the questions if you like. So what do we actually start with? Well, we start with the kind of abilities that you see in this 1.5-year-old here, playing with blocks or stacking up cups, the ability to understand object permanence, understand objects as real things in the world, and something about their physical properties that allows him to imagine this plan where the cups can fit together. They can make an increasingly tall tower. You can see him sort of formulating in his mind a plan to make a little stack of 2 cups, which he's trying to put onto the stack of 3 cups. And notice he makes some mistakes, and there's also some bugs in his plan, but he's able to debug and fix his plan. And it's really impressive what he has to understand about these physical objects and their dynamics that allow him to conceive of and execute and fix these plans. Um, if we could build robots that had that kind of physical intelligence, it would be amazing. There have been great advances uh, in here. I'll just let him achieve his goal and then pause with him there. Okay, very impressive achievement. If we could get a robot that could do that and be as proud of it as this kid was, that would be quite an advance in AI. We're not there, but I think we can. We're moving in that direction. Um, by intuitive psychology, what I'm going to show you here. This is a video from a very famous set of experiments published a little more than 10 years ago by Felix Warneken and Michael Tomasello. And these were scientific studies of 1.5-year-olds. And an example participant is the kid shown in the back there. Um, the experimenter, Felix, is this guy in the foreground. And what you see here is, what the kid is seeing is somebody doing something that you've never quite seen before. But when the adult stops, the kid is able to figure out what he's doing and why, and even how to help him. And you can see he does something very helpful here. Okay. Let's watch it again now that you've seen it, and think about what has to be going on inside the kid's head to be able to do this, to be able to see an action you've never seen and figure out what somebody's doing and why. You have to think about the physics of the cabinet thing that's blocking him. You have to think about what possible goals might be. You don't know what's behind the cabinet door, but when you open up that cabinet door, you see something that makes sense. You see a shelf, and you can imagine, a possible goal of putting the books on the shelf. So you move back, get out of the way in order to do that. Now watch it one more time, and I'll just jump right to the end. Watch at the end when the kid steps, he makes eye contact, and then he steps out of the way, that step back, right? And that eye contact. it's as if, and I think more than as if, he really knows what's going to happen. He thinks, if I've understood you correctly, I think I know what you're going to do. You're going to move in this direction, and I have to get out of the way because you're going to come in here because you're going to put those books down on the shelf. So our goal, again, suppose we could build robots that could do this, be this helpful around the house or in other settings, it would be amazing. Um, our goal is to build the kind of engineering competence, knowledge representation and reasoning, and effective inference algorithms that can do this. So the pictures I'm showing here are sketches of the models that we build in our group, which are our scientific models, our engineering style models of the mental models inside these kids' heads, of intuitive physics, how the state of the world changes over time and gives rise to the images we see. Or on the intuitive psychology side, what are the mental states inside an agent's head, their beliefs and desires or beliefs and goals, which produce actions via some kind of efficient planning process, changes the state of the world, and the agent updates their beliefs via perception. This, the model on the right is like a classic kind of rational agent model. And without making any statement about whether that's the way human brains actually work, it's the intuitive theory of how human minds work, and we can capture it in computational terms. That's what we're trying to do in the work I'm talking about here. Okay. So how are we going to do this? How are we going to build models of these mental models? Well, the first step is that we need the right knowledge representation frameworks and reasoning frameworks. And for us, we've been working within the context of what's called probabilistic programs or probabilistic programming. For people who are more familiar with logic programs, including Prolog or inductive logic programming, there's a lot of commonality here. Like the logic programming approach, we are taking symbolic languages for abstract knowledge representation reasoning as probably our central driver here, but thinking of our reasoning framework as coming more from a probabilistic or Bayesian approach, because we especially want to build symbolic languages to capture causal models like physics or the planning processes inside somebody's heads. And that we want to have an inference framework which can support seeing, say, the outputs of these programs, like the output of physics, what things look like as they change over time, and work backwards and reason backwards to the underlying causes, and then make predictions forward or make action conditional predictions, evaluating the possible effects of our plans. Or likewise, for understanding the internal mental causes of somebody's actions, the inputs to planning programs like beliefs and desires. Okay. So we do a lot with integrating these symbolic languages and probabilistic inference. And broadly speaking, that's what probabilistic programming as we use it is offering. But we're especially interested also in what are sometimes called a modern generation of probabilistic programming languages, like the ones I'm highlighting here in bold on the right: Pyro, TensorFlow Probability, Gen. The tradition of building probabilistic programming languages that allow you to declaratively specify a symbolic probabilistic model and then do inference with various kinds of general purpose inference algorithms, goes back, probably 2 decades now, but especially has been really active since the mid 2000s. But these more recent languages also build on top of modern deep learning frameworks like TensorFlow or PyTorch. And that gives you an integrative approach where you can also use the things that neural networks are good at, because pattern recognition and function approximation are probably also part of intelligence. I don't want to deny that. In fact, I want to celebrate that and figure out how to use that and integrate that approach with the best of these other ideas of intelligence that we know, are not necessarily the idea that the press is writing about most, but are just as if not more important. Okay. If you'd like an introduction to probabilistic programming, if you're not familiar with it, the probmods.org webbook, which is like a very basic, lightweight textbook style introduction that was written by Noah Goodman and me and a number of other colleagues, is a good place to start with a lot of interactive examples. If you'd like an introduction to the Gen probabilistic programming language, which was developed by Vikash Mansinga's ProbComp group at MIT, and I'll show you one or two examples of things that we've been doing collaboratively with ProbComp using Gen. Because to me, Gen is a language which I think is specifically designed to get at the kind of common sense representations and reasoning that we're doing here, and really scale up what I'm going to be talking about to the level that will have significant technology payoffs. I would very much recommend checking that out. It's gen.dev is the website for that, and there's some tutorials there, and you can teach it to yourself if you're interested. All right. So these probabilistic programming languages are, I think, the main driver of the work that we're doing. But then we have to talk about what kind of programs are we going to be doing probabilistic inference about. And to capture this core common sense state, like the earliest intuitive physics and intuitive psychology, here we have been making some interesting new uses of game engines. And I lump these under the phrase the game engine in your head. So I want to illustrate this idea. Because again, I'm sure probably most people in the community here are familiar with game engines. You might not think of them as knowledge representations or as the basis for a reasoning engine, but that's exactly the way we're trying to use them. So game engines are these tools that were developed in the game industry for, to allow a game designer to create new games very quickly without having to write everything from scratch. And especially to create a rich, immersive, interactive experience like in a 3D world for a human player that might have compelling graphics, compelling physics, so that if I drop an object, it falls. If I let go of, if I'm holding an object and I let go of it, then it falls. Or if it's made of glass and it hits a hard ground, it might break. Or if the glass contains some water or some poison or some acid, it might spill out, or I might be able to pour it by tipping it the right way. Okay. The ability to have what feels like an immersive, open-ended, interactive experience requires some kind of rich modeling of what the world looks like, how light bounces off of surfaces in the world. That's very general, and also the dynamics of how things move and interact, so that players can just do anything, so to speak. Also, what's called game AI, which is not really AI, right, but is simple forms of agent modeling that allow non-player characters in the game to interact with the human player in somewhat flexible, open-ended, plausible ways. So simple kinds of perception and planning algorithms that give agents in the game like line of sight access and shortest path planning, very simple kind of goals and sub-goal planners. All of these tools together, I think, provide an interesting hypothesis of what kinds of core knowledge might be present in very young babies. And then the question is, can we wrap those ideas inside frameworks for probabilistic inference in order to capture common sense reasoning, at least the core common sense reasoning? If you're not familiar, I mean, I'm sure many people are here familiar with game physics engines. This is just a sample of some of the rich kinds of things you can model with these systems, not just, rigid body systems, simple ones like a few balls bouncing in a box, although you can certainly do that, but really complex systems of many, many rigid bodies, or these chain link things like the wrecking ball hitting that set of many, many cubes, or soft bodies like cloth interacting with rigid bodies, or fluids with particle systems, snow, water, and the like. Okay. And all of these things, they have some physical reality to them, but they're not designed to be maximally accurate. They're just designed to look good, to look right on short timescales, and to be flexible and general, and to be very efficient, to be able to run in real time or much faster than real time. And all of those design characteristics, they're useful for video games, but they're also, I think, useful for cognition. And though I'm sure this hypothesis is wrong in all sorts of ways, I think it might be an interesting, at least, starting place for what might be built into the head as part of a general, let's say, intuitive physics engine. Okay. Or at least a starting point. When we say this is the game engine in your head, partly we also want to distinguish this from the way game engines have been used in other areas of machine learning these days, and AI, like in reinforcement learning, where you see the game engine as the training ground for an agent, like a robot that's then going to be deployed in the real world, and you have some sim to real problem. The game engine isn't the training ground, it's a model of what's inside the agent's head for us. So when this kid thinks about, I wonder what will happen if I roll this ball forward along the floor towards this stack of wood blocks with the toy bird on top, what will happen? Maybe something like this will happen. I run a simulation in my head. I can see the ball hitting the blocks and them falling over in some ways, and then that's either what I want or what I don't want. And depending on that, I can take my action or revise it accordingly. So the game physics engine as an approximation to the approximate physics models in our heads. So taking these two ideas, something like approximate simulation, which we can then wrap inside a framework for probabilistic inference, we've used these tools to capture some of these basic core common sense abilities over the last few years. So going back now almost 10 years, working with colleagues, starting with Peter Battaglia and Jess Hamrick, who were in our lab at the time, published some of the first papers on this approach to thinking about intuitive physics. And a number of other colleagues since. I'll just show you one of our earliest experiments here, because I think it's still the easiest way to see how we use these tools. we study situations like these blocks world scenes, where in a glance you can look at these stacks of blocks and think of them as like wooden blocks, like in the game Jenga. We give people a little bit of familiarity with these objects, and we show them a couple of scenes of interaction, and that's enough to really know what's going on here. But looking at these scenes in a glance, you can see that some of them look stable, and others, like the ones in the lower right, look like they should be falling over, very unstable. So how do we capture that kind of ability? We need some way of taking an image, working backwards to infer the underlying world state, which then provides the basis for some kind of physical prediction. And we can think of programs which capture these two different causal arrows here. But what we're calling graphics, which is what you have in a graphics engine, in a game engine, that's a mapping from the underlying 3D world state to an image. And then that world state also, though, provides the state of the mental physics engine. So to be more concrete, if we see an image like this, we see that as the output of some kind of approximate renderer, which takes as input a 3D scene description, like some kind of CAD model of the objects in the scene. And we want to make a guess backwards to infer what is the likely input to that graphics renderer. This is the idea, which is again a very classic idea of what's sometimes called vision as inverse graphics. It's related to the idea of vision or perception as analysis by synthesis, if you've heard that phrase. And we've, together with some of the colleagues I've already mentioned and some others, Vikash Mansinga, but especially Tejas Kulkarni and others, again, over the last 5 to 10 years, we've been building increasingly general probabilistic programming language frameworks for solving this problem, where you express forward models or graphics programs with the right kind of tools that allow you to make Bayesian posterior guesses on the likely inputs under some kind of prior on scenes, the inputs which best explain the observed image under some kind of sensible likelihood function. So what I'm showing you here on the left is one actually example of a sample from the Bayesian posterior in a scene prior that says we have blocks of these, basically we have scenes made out of these Jenga blocks that are in one of either a horizontal or vertical orientation and in contact with each other. And this is one possible explanation of this scene. Here's another possible explanation, a slightly worse one, but also a more relatively plausible posterior sample compared to all the other ways you could imagine the blocks might be configured. Right. So what we aim to do is to have inference algorithms which can take this approximate graphics model and make good guesses, good posterior guesses. We can use a range of different inference algorithms. The classic probabilistic programming approach is building on the successes in Bayesian statistics with Monte Carlo inference, like MCMC or Markov chain Monte Carlo. These are effectively, you could think of them as top-down approaches, which make guesses on hypotheses and then local adjustments and check them and score them and see whether that local adjustment has made things better or worse in terms of how well, when I move the blocks around in my CAD model, how well does it fit the image. We tend to accept proposals which make things better. And if you're willing to wait long enough, that's going to give you a reasonable sample of posterior interpretations. But it can be quite slow. So there's been a lot of interest in how we can make this faster. For example, by here using neural networks, where we might use our simulation model to generate training data for a neural network by imagining possible scenes, random scenes, imagining what they look like as the images, and then that provides supervised training data, pairs of image and scene, top and bottom in this view, that you can train a neural network, or what's sometimes called amortized inference, to invert that causal arrow and at least make good posterior guesses, which can then, for example, in a hybrid approach, be cleaned up by an MCMC approach. So whether it's what's called data-driven initialization or data-driven proposals, where your MCMC proposals, your ways of adjusting the scene are driven also in a bottom-up way by some neural network, for example. This can, as I'm showing here, this is from the work of Kulkarni et al. From a few years ago in CVPR, can lead to inferences which are extremely accurate, that's the blue curve, as or more accurate as a pure top-down MCMC baseline, but much, much faster. And increasingly, models like this are being explored as candidate models for how vision works in the brain. Just briefly, the latest work on this, which uses the Gen language, which I mentioned before, this is from a paper to be presented just next month at the NeurIPS conference, coming from Vikash Mansinga's group, and it's the work of Nishad Gothaskar and Marco Cusimano-Towner and others. And here, what's exciting about this is that our probabilistic programming languages for scene perception now are mature enough that we can deploy them in real world robotics type settings where we have, real RGB data and depth camera data, and for a range of complex real world objects like the scenes shown here. And the system that they've built is able to infer the 3D poses of these objects, as well as a kind of a scene graph structure, so capturing the qualitative relations of what objects are supporting or in contact with which other objects. And then that's also used to take the sort of noisy depth image, and you can reconstruct a much more accurate depth image, which would be essential for robotic interaction tasks. And so Gen, this new probabilistic programming language, allows us to write a rich probabilistic model that starts off by sampling possible kinds of objects and their 3D shapes, then their scene graph relations, and it renders that down to a depth map image. It doesn't, the graphics model doesn't go all the way down to pixels. It goes down to some kind of depth map, which is a convenient intermediate representation to compare with the bottom-up sensor data. And then the probabilistic programming language gives you a range of automated inference tools. It's not just a one-click thing, just give me uh, give me posterior samples, but rather lets you engineer combinations of, for example, neural impedance sampling and MCMC fine tuning. But it gives you a high level language in which you can write powerful inference algorithms that combine neural net learning with top down MCMC based adjustment very efficiently, both efficient to write and very efficient to run, and produces significant advances on the state of the art of just pure deep learning based object detection. So that's all I'm going to say about this, but it's just, if you're interested, check out the 3DP3 paper from Gothaskar and colleagues at NeurIPS, or it's online on Archive, and it just shows how this toolkit is now maturing into a powerful, actually, engineering approach. Okay. But back to the cognitive science, and beyond just seeing the scene of the world, if I want to make a physical judgment, I need to be able to say not just what the scene looks like now, but what's going to happen in the near future. And here are approximate physics models that we can instantiate in standard kind of game engine physics, like PyBullet, for example, allow us to take a scene guess. This here is one of my posterior scene samples, and run it forward through the physics engine. Maybe with some uncertainty about which forces are in play. Like, I may not know exactly how strong friction is, or I may allow for the possibility of wind or other sort of forces beyond just the ones I know how to model, like gravity, friction, and so on, and forces of collision. But those are the basic kinds of forces that we're trying to model. And I can run a simulation forward a few time steps from this initial guess, um, of the state of the blocks, and I see that what happens. In this case, most of the blocks have moved or fallen somehow. Here's another simulation where I took my other posterior guess and ran it forward. And what you can see is that the end result after a few time steps is different, right? On the upper right, we see very different things here. But at the level of intuitive physics, it's basically the same. Namely, all or most of the blocks have fallen over. And so that's what matters in our models of intuitive physics, and what I would argue common sense needs. It doesn't need to know exactly where everything's going to go, and indeed that's almost impossible to predict. But taking just a small number of samples of a few time steps of simulation from a few different initial conditions is enough to make a good guess, and to have some degree of confidence or error bars. And what I'm showing you here is now is using that as a model of human judgments. So on the x-axis, the model predictions is the average number of blocks or proportion of blocks that have fallen in a couple of simulations for any one of 60 different tower stimuli, following the pipeline I just showed. On the vertical y-axis is the average judgments of a group of humans, where they're asked to rate on a scale of 1 to 7 how stable or unstable is one of these scenes. And high up or far out on the right corresponds to very unstable, very, very likely to fall. Low down and on the left is very stable. And what you can see is this model does a pretty good job of capturing people's judgments. There's a correlation of around 0.9, or it accounts for about 80% of the variance. And you can compare that with an interesting kind of baseline like this one, which is exactly the same physics model, but with no uncertainty, no probability. And I point to this to show why we need to be thinking about probabilistic reasoning here. We need to be thinking about knowledge representation, which is basically a certain kind of symbolic approximate physics, but embedded in a framework for probabilistic inference. Because in real world common sense settings like these ones, there's always going to be some uncertainty of exactly where the blocks are and maybe what forces might be in play. And that allows our model, the one that I showed you before, to do to capture people's judgments, and we argue to be more useful in the real world. The one here, which you can see captures people's judgments less well, has the same physics but no uncertainty in the state and no uncertainty in which forces are in play. So in some sense, it's more accurate in the ground truth sense, but it's less accurate as a model of people's intuitions. And you can see that when you look at points like this red dot here, which corresponds to this stimulus, this is one which people judge to be extremely unstable, very high up here, and the probabilistic model also does. But the ground truth physics actually says it's completely stable. Namely, none of the blocks, zero of the blocks, are moving under gravity. It's just precisely balanced, that nothing is actually going to fall over. And there's a number of other stimuli in our experiment that are these kind of stability illusions. All these points here correspond to things which don't actually move. They're completely stable, but to more or less degree, people judge as being unstable. And our models suggest that might be because they're taking into account some of the probabilities that I've raised. Whereas if you don't take into account the possible ways the world could be a little bit different based on what your perception specifies, then you actually, you know, fit people's judgments worse. Okay, so this is just one illustration of ways we've used these ideas. We could, the same, a part of the power of probabilistic programming as a framework for knowledge representation and reasoning is that just like with, say, a Prolog type model, we write the physics model declaratively, and then we can query it in any number of ways. So we can ask, what I just did is, how likely is the stack of blocks to fall? Or what's the expected proportion of blocks that will fall? But also, which way do you think they'll fall? Where do you think the dominant axis will be? Or how far will they fall? Or we can change some of the variables in the program. Like suppose I tell you that the gray stuff is much heavier than the green stuff. How does that change your judgment? Notice these stacks here have the same geometry, but we've just recolored them. And if you know that the gray stuff is a lot heavier than the green stuff, it'll change the direction of fall for both you and for the model. If I show you these scenes, which are surprisingly stable, then you might be able to infer that something is much heavier than something else. Or I'll just show you one other example, which is an example I like to show about intuitive physics because it's unlike these questions of like how likely are the stack of blocks to fall. These are questions which, unless you've seen me give this talk before, you've probably never done this task, right? Because I'm just about to make it up and tell it to you in natural language. In contrast to, say, judging stability, which is something we do since early childhood. But you as an adult can ask this question and answer it. I say, imagine the table is bumped hard enough to knock some of the blocks onto the floor. Is it more likely to be red blocks or yellow blocks? And I could show you many situations where you just know the answer pretty much right away. So here I'd say, okay, I imagine it would be red blocks. Here I might say, well, yellow blocks. Here probably you'd say red blocks. Here yellow. Here yellow. Yellow. Probably more red, you might say. Here yellow. Um, it'd be more fun to do this interactively, as I usually like to do in talks, but hopefully what I'm saying accords with your intuitions. And the way we model that is by running a simulation of a bump of the table. Like here's one of those scenes reconstructed in our game physics engine, and I can run a few time steps of this simulation with a small bump, and here's another simulation with a big bump. And I'm stopping them each after just a few seconds, or just a few time steps, so that you can see, first of all, that again, it doesn't really matter whether I do a small bump or a large bump. The actual outcomes are different, but the statistical properties, which I'm going to measure in my intuitive physics, are the same, namely all or most of the yellow blocks and few or none of the red blocks are going over the table. And also, you don't need to run this simulation all the way to the end. Just a few time steps is enough to be able to see what's going to happen to evaluate that query. And also, it doesn't have to be especially accurate because, again, the precise details don't matter. So you take a small number of short simulations run from a couple of different initial conditions, and that gives us the model here, which is, again, I'm showing a plot of human judgments on the y-axis and model judgments on the x-axis about percent red versus yellow. And you can see that it's almost as good, not quite as good, but it's almost as good as the model of stability judgments. And that's striking because if you think that it's something like experience-based learning that's driving this, or like if you were to take a reinforcement learning or any other kind of supervised learning approach, these should be very, very different tasks. Like this is not something that you've had any practice with. And yet you can still apply your intuitive physics basically just as well. So again, to some extent, I think I'm kind of preaching to the converted here, or the prophets. But as an argument for why you want to have some kind of model-based approach to common sense reasoning rather than something based on learning from data, this approach, which did absolutely no learning, I think is a good way to think about it. Now, I talked about intuitive psychology, and it's a big part of the work that we do. I'm not going to spend any time on this because I want to spend some time talking about learning, as well as especially ways that we build more symbolic kinds of reasoning and learning on top of this basic common sense core. But just to point towards where this kind of toolkit can be used and how you can build on and extend these probabilistic approximate physics models is to say, well, if I want to build a model of what makes of how how I understand somebody's goals from seeing their actions, the output of a planning algorithm that takes as input something like their beliefs and based on what they can see and their goals. The basic idea, which again has a long history in studies of intuitive psychology in young babies, is what's summed up by my colleague Julian Haar-Enninger as the naive utility calculus. The idea that this is intuitive in even young children's and infants' minds, that there's some kind of reward cost calculus. Rewards get assigned to states that are goals. That's what it is to be a goal. Costs get assigned to actions, and you make plans that maximize your expected utility of the reward of getting to a goal state minus the cost of action. And then if we have some hypothesis space and priors on the possible rewards or states that can be rewarding, and some model of cost, then that provides the forward model, actually the constraints that a planning algorithm needs to produce actions that then lets us work backwards and make probabilistic inferences on an agent's likely beliefs and desires. And we've applied this in many ways, but for example, we can also take video of somebody reaching for an object, like you see here, and judge like which object do you think she's reaching for. Maybe around now you have a pretty good sense, and if you are like me, you were right in that case. Initially, you couldn't quite tell, but after a little bit of time, you could tell. And what I'm showing you here, this curve is the corresponding Bayesian posterior in our model that roughly captures, I think, the inferences you're making, where the costs here are driven by a physics engine, because ultimately we act in the world. And so the costs come from physics and the constraints of our body. We use the Mujoko physics engine for robotic motion planning to compute the costs of different um, plans. And then also we can use this to figure out efficient, cost-efficient plans towards the different possible goals. And that provides the forward model, which we can then again sort of run in reverse by doing approximate Bayesian inference to figure out the most likely desire or goal input to that cost-sensitive planner. And we can also extend this to a multi-agent setting, like this one here, to be able to make sense of, why does this action here look like somebody's helping someone else, especially like it's a sort of a weird physically constrained reaching, and you get a sense of what the person is reaching for, as well as that somebody else is trying to help them. Or here, with again a different set of physical constraints, you get a sense what somebody is reaching for and that somebody else is trying to hinder them or get in their way. And we can model that by taking a recursive utility calculus, basically, to have an agent who, what it means to be helpful is to be acting under a utility function that takes your expectation of somebody else's expected utility as an input. To be hindering is to take somebody else's expected utility as a negative term in your own utility. And that's an abstract definition of the concept of helping or hindering, which can then be grounded in one of these probabilistic programs so that we can see a set of actions and work backwards and say, what kind of utility function do I think this agent is doing with respect to another agent? And that's how I'm able to infer whether they're helping or not. So that's all I'm going to say about the core notion of common sense. And I want to spend the last few minutes talking about learning. Okay, where does learning come into this picture? So one possibility that a lot of people are interested in, is again, it's sort of the latest version of the approach that Turing might have advocated for, is to say that these systems, maybe these are the targets of learning. And well, it's not fair to say this is what Turing suggested, but at least one interpretation of the Turing sort of blank sheet approach, right, is that this is what you should be trying to learn. And to a deep learning person these days, you might say, well, let me see if I can learn end to end from raw pixels what is needed to support this kind of intuitive physics of objects, for example. So here's some nice work along those lines by Nick Haber, Dan Yeamans, and colleagues from a few years ago, in which they try to learn sort of very basic aspects of intuitive physics of objects. And I think it's a nice idea the way they do it. They have a kind of a curiosity-based deep learning RL system, but I don't, I think it's an interesting thought experiment, but I don't think it is ultimately a scalable approach or the way that it actually works in humans, because it doesn't build in nearly enough of what we seem to see in the youngest babies. This system takes a very long time to learn things that seem to be present very early. So the approach we follow is to look at all the different ways that learning can work with this idea of something like, for example, a game physics engine. Ways that learning can learn things that go on top of it, or learning inside the game engine, or maybe even learning the game engine itself. So one kind of learning, and I've mentioned reinforcement learning a few times, I think deploys in a really interesting kind of reasoning setting. Human reasoning and learning really aren't opposed. A lot of our reasoning is the result or is part of, let's say, a kind of a trial and error process where we do some reasoning, we think about what is the best thing to do, we try it out, and if it doesn't work, we try to debug our plan, as I've referred to a few times. And then with some experience, we might learn some kind of plan templates that we can then reuse much more easily rather than having to solve those problems from scratch again in each new situation. And we've been really interested in what kind of learning and reasoning approaches work there. We've been studying this particularly in the context of intuitive physics, where the physical problem solving comes up in the context of tool use. So here I'm referring to some recent work by Kelsey Allen and Kevin Smith from our group. In what I'll show you in a second, is the virtual tools game, but it abstracts from the problem of, like, let's say I find myself needing to put up my tent on a camping trip and I forgot my hammer to hammer in the tent stakes. I might look around for other objects that I could use as a tool to achieve my goals. I might fairly quickly rule out some of the things that just don't seem to have the right physics, but then of the different rocks that are sort of hammer-like, I might try, say, for example, this one, realize that no, that doesn't give me maybe enough leverage or something like that, and switch to this more elongated one down there. Okay. So the way we try to abstract that in a game, and I realize this one's slightly out of date because it says in press, but this paper appeared in 2020. Um, I'm showing you a couple of scenes from this virtual tools game where the player chooses a tool object from one of the three shown on the right and then drops it into the scene. Blue objects just sort of move under standard 2D physics. Black objects are stationary. The goal is always to get the red object into the green region. But depending on the scenario, on the level of the game, there are many different kinds of strategies that you could use. So if you watch some of these other scenes here, you'll see some of the possibilities, whether it's blocking, preventing objects, or catapulting, as you see down here. This scene, which is doing some kind of, where you can see that's not a very good strategy, this one in the lower right, but after a couple of trials, the player will figure out something better that involves kind of making sort of a stable table-like support. Just see one more of these scenes. You can see how they're kind of exploring the space of possible tool use strategies and kind of debugging their plan. Or here, this one is one of the most interesting ones where they have to realize they try to use objects to knock this object in, but because of that blocking object, the simple things aren't going to work, and ultimately you have to figure out, I'll just jump ahead here, a kind of a hooking strategy like this. But then once you figure that out, you have to generate enough momentum, so you have to realize the relative height from which you put this object. So that's the basic idea of the tools game. And we could build a simple model which takes the approximate probabilistic simulator that I've suggested here as the basis for sort of mentally trying out different possible plans, where we initially sample an object and a placement in the scene from some very generic prior, which just says, put something in the scene somewhere where it's going to hit something else, basically, cause some effect. You try out a few possible plans like that and see which ones might be likely to work. If they work, and then if you come up with one in your mental model that seems like it's likely to work, you try it out in the real world. If it doesn't work, you try to update your prior based on that in a relatively simple way, taking into account like how close you were. That's the basic logic of this sample simulate update model. And across a range of different levels, it does a pretty good job of capturing people's learning curves in these tasks. What these curves show is the cumulative probability of success in one of these tool use tasks for each of these different levels. comparing people in models, like how many trials do I need to achieve a relatively high probability of success? This is a kind of trial and error learning in that, each one of these trials is one failure of an action in the world. But it's not what people talk about as trial and error in reinforcement learning, right? This is like learning from just a few trials, at most 10 or 20 here. Okay. And the model is able to capture this very rapid kinds of trial and error, almost sort of debugging process, in ways that are surely missing important things from how humans think, but it's taking us a step towards, I think, the real kinds of physical reasoning that people do. You can add on to this an interesting symbolic layer, which is needed to capture really the more abstract concept of a tool. So if I want to know, what is a whisk or what is a hammer, or I showed you a catapulting scene, but what is it that makes any of these things look like catapulting? Whether it's a catapult that launches someone into a lake, or a pandemic catapult that you can make in your kitchen to put a rolled up piece of paper into the trash bin, or the kind of catapulting that we saw in the tool use game. There's some abstract concept in common. People can learn these abstract things, which I didn't show evidence of this before, but we can also give people sort of multiple kinds of examples of catapulting, and they can learn and transfer to very different situations these abstract concepts. And we can capture that by just replacing this prior, which was just a very simple physics-based prior, with a learned symbolic program strategy, which here this is a probabilistic symbolic grammar that references objects of different types, their properties and relations to other objects, and uses that to formulate a space of possible strategies which can capture simple versions of like the catapulting concept. So here's an example of a hypothesis that is formulated in that grammar and learned from a small number of successful problem solving strategies that capture roughly what it means in a very simplistic way, but what it means to do a catapulting strategy in this game. And this symbolic program can be reused quickly in new situations. That's one kind of symbolic knowledge-based learning that can go on top of core intuitive physics. Another kind is actually trying to learn something about the physics, right? So whether it's this kid playing with an air hockey table, or scenes like these where we show in an experiment with adult, this is work from Tomer Ullman and colleagues, um, where you're like looking down on an air hockey table and these pucks are bouncing around with perhaps unusual kinds of physics, forces of attraction or repulsion, or um, wind blowing one way or another, or various different masses. Some are heavier, some are lighter. People can look at even just these short videos and make judgments about the latent properties of the objects, their relative mass or friction, as well as what forces are in play. And in the work we did a few years ago as a model of human learning here, we captured this with a hierarchical Bayesian approach in a symbolic physics generative model. So we basically give our system Newtonian mechanics, and then we have it make inferences about the parameters which correspond to the force laws or the mass and so on. And it can make reasonable inferences that roughly correspond to the ones that people do from just 5 seconds of a video. In another kind of recent update, here's another paper to be presented this year at NeurIPS, which Tomer and I were both collaborators on, although it was mostly the work of Kai Shu and Akash Srivastava. Um, it sort of extends this kind of idea to basically build in Newtonian mechanics like F equals ma and the idea of pairwise forces, but then search through a space of possible force laws that could describe different physical situations, guided by certain basic semantic constraints that are what physics tells us, like dimensional analysis, the units have to work out, and translation and invariance. So we're only going to consider possible force laws that respect those constraints. But this system now can be given a range of different scenarios, including also real video scenarios, like video of somebody dropping a ball onto a table. Um, and infer a kind of basically a gravitational force that together with F equals ma explains the trajectory of the ball. Or having done that, we can then show it something like an object kind of bouncing around on a spring, and it can learn the extra force law it needs, which is something kind of like Hooke's law. So again, these are just sort of steps towards how you might take a probabilistic symbolic approach to learning now some of the basic components of a mental model of physics, or the same kind of idea we think could apply to planning or other core common sense systems. All right. The last thing that we might just want to look towards is not just learning, a single bit of code, but how might we learn more richly? Like, how might you learn an entire intuitive physics engine or some common sense domain theory? Intuitive physics is one of these domains where over the first year of life, infants really do learn a lot. And I'm not this is just a high-level review of some of the things that infants seem to learn at different ages. And we might ask, could we build a system that effectively goes, posits a probabilistic intuitive physics simulation program at any one of these stages, but kind of grows out that code over time based on limited amounts of experience and trying to make the model better. Effectively, we're asking about another sort of grand challenge of AI, which is the idea of learning as writing code and even writing large bodies of code. This approach to learning as programming effectively is one that also goes back to the early days of the field. Like think of like Solomonoff induction, for example, or work of John Koza in genetic programming, or many others. Um, and it's a very hard problem, as we all know, because unlike learning in the space of a neural network, learning in the space of programs, if we want a learning algorithm whose outputs are programs, there's nothing like a nice topology or smooth geometry that lets you do gradient descent. But somehow we think if the state of knowledge of a human being is something like a set of programs, then learning has to have some effective way of searching through spaces of programs. And recently, this is something that we and others in computational cognitive development have been especially interested in as a unified, overarching way to at least formulate the hard problems and maybe some of the solutions in cognitive development. We recently wrote an opinion piece here. Josh Rule and Steve Piantadosi are the leaders of this effort, that we called "The Child as Hacker," and by that we mean the MIT version of hacking, not the bad guys who break into your email and steal your credit card numbers, but the clever, creative exploration of the world through code, as we call hacking at MIT or in other areas of computing. And this general idea that our best universal representation for knowledge is code, and then learning is all the things we do to make our code better. So looking at all these different areas of human knowledge, which at this point can be expressed in different kinds of effectively symbolic languages, and looking at all the different approaches that we do when we are working on our code as programmers or software engineers, all the ways we don't just tune the parameters of existing functions like in learning in a neural network, but all the ways we learn by writing new code, by adding functions, by debugging functions, by writing libraries, maybe even writing whole new languages. So think of this as a white paper or a polemic or something about what the future of the field of learning should look like. We're very far from systems that can do any of these things, but it's just as one more example of recent research that's come out of our group, and that other kinds of things that many others are working on at the intersection of machine learning and programming is systems like this one. This is a system called Dreamcoder that was the thesis work of Kevin Ellis with a number of other collaborators, especially Kathy Wong, and it was really interesting, exciting interdisciplinary work that I feel very privileged to be part of. Kevin was a remarkable grad student who really synthesized the kind of approaches that our group has developed with the toolkits coming out of the toolkits for program synthesis and program analysis that come out of the programming languages field, which again hasn't been really thought of as a branch of AI or machine learning any more than like game engines have been thought of as a knowledge representation. But I think many people are increasingly realizing, whether they're coming from like the KR field or the PL field, that these fields have a lot in common. So what Kevin did, and by the way, Kevin's now a assistant professor at Cornell in CS. He's just started there. Is he built the system that he calls Dreamcoder, which I'll tell you in a second why it's called Dreamcoder. But the basic challenge is to try to scale up this idea as learning as programming by taking a number of different domains. We look at 8 in this paper. And in each domain, there's a number of problems to be solved. Each problem can be solved by writing a little chunk of code, or at least if you have the right domain-specific language, the problem solution can be expressed as a short program. But we start off with a very generic language, and that means that, like some very generic functional programming language, and that means that initially most of the problems can't be solved because the expression would be way too long. So for example, if our problem is to sort a list, in the initial language that we start off with, this would be very, very long. I'll show you in a second. But over time, by solving problems, we actually expand our DSL. We find new candidate primitive functions to add to our library based on finding shared motifs in the problems that we've solved before. So we wind building a kind of deep library of concepts, which are new functions that can be defined on top of our original DSL plus a just generic lambda calculus function constructor. So that allows us to come up with, let's say, a sorting program like this one, which is quite short, but it uses derived or invented concepts that themselves are based on earlier layers of invented concepts. The original language, if I were to write this sorting algorithm in the original language, it's very, very long, and I would never have found it by any kind of reasonable search. But after having built up this learned library, now many, many problems have short solutions because I've learned the right concepts that are appropriate for this domain. The algorithm is called Dreamcoder because it learns with a kind of wake sleep learning, and I'm not going to tell you, I can't tell you any of the details because I'm basically just about out of time. But the key is that there's two kinds of learning. One is as a symbolic approach that I talked about, which is basically takes solutions that are found during the waking problem solving stage and does some refactoring to expose shared primitives that then become candidates for new primitives in the language. And the metric for learning there is just like a compression score, or it's like you can think of it as learning a prior in a hierarchical Bayesian sense. So that means we're basically trying to find a probabilistic grammar on programs that makes the programs we've learned so far short or high probability. So that learning as compression idea lets us find the right new concepts. There's also this dream phase of learning in which, like other kinds of wake sleep learning, if you've heard that idea, we imagine, we kind of invent random new problems to solve that then can be used to train a neural network, a pattern recognition system, which guides the search. There's still this really hard search problem, even when you've learned a good DSL. And in some sense, the search problem gets harder because the bigger your library gets, the broader the search tree is. But we can, by generating synthetic problems to be solved, we can use pattern recognition to learn the more kind of implicit procedural expertise that might be the sort of thing which also is part of guiding human problem solving, in addition to the more explicit declarative knowledge of the domain that's captured in the learned library. So as an example of that, for instance, we might apply this to, say, tasks of like building towers or drawing things, where we might start off with like a very simple logo drawing language, just like turtle graphics, pen up, pen down, turn, go forward, plus lambda calculus. That's not enough initially to be able to find short programs to make even these simple drawings. But over time, we start off solving the simplest problems, and then we learn a library of drawing primitives. And it's shown here as one of these deep libraries, such that even more interesting complex drawings have short programs. And when we look at the dreams of the system, and the fantasies that it makes up, right, early on at learning, all it knows how to do is make very simple lines and arcs. So its imagined problems aren't very interesting. But after 20 iterations of building out the library and building more expertise into the neural network that guides the search, its dreams are much more interesting because of all the stuff that it's learned. So it shows a way of perhaps scaling up this idea of program learning, whether it's to learn a language for drawing or actually the same kind of thing can solve a bunch of different physics problems and learn something like a language of physics. This is the sort of, uh, I think, approach that can give us what we really need for the roadmap of human cognitive development that goes beyond that core state of intuitive physics and so on to all the things that humans learn beyond that, especially learning language, which learning to speak and talk to each other, which grounds out in our basic concepts of objects and agents, what can happen and what plans people make. But then once we have language, we don't just talk about the things in front of us, but we can read, we can learn about all the stuff that humans have discovered culturally, knowledge that's accumulated across generations. And that's the real singularity of human intelligence. So we're not there yet, but hopefully what I've suggested here and shown some first concrete steps is a roadmap for how we might actually build a machine that grows into intelligence the way a person does. And that starts from recognizing that a lot important kinds of representation has to be built in, and the learning mechanisms have to be much, much smarter in a sense than just standard kinds of statistical learning or reinforcement learning. All these ways in which we're using both the idea of probabilistic programming for inference and program induction and program synthesis combined with the right kind of starting programs, I think it's still very early days, but it's exciting to see where this is going. And I hope the KR community will be interested in engaging also with this research program. So thanks very much.